We have been studying clinical trials for some time now. Clinical trials are considered the gold standard of study design, in the sense that there are many facets in the design to guard against any kinds of bias. Any kinds of bias in allocation as well as any kinds of bias on part of the subject who is undergoing the treatment under consideration. However, an interesting twist is given by the fact that we are dealing with human populations and that there are some additional ethical considerations in dealing with such populations. Now, there is a very interesting ethical dilemma which arises when we see, even before completion of the trial, that one treatment is clearly superior to another. Of course, the fact that clearly superior must be in quotation marks because the trial is not yet completed and I cannot draw any conclusions with my allocated power. However, it is an interesting poser to the physician, and he needs to decide whether or not he should continue to allocate at random or whether it is at all possible to allocate more patients to the treatment which appears to be better, but without compromising the scientific principles of the study. So this is what we will visit in this module, which is entitled Play the Winner. In this module, we are going to study the Play the Winner rule. We will mostly follow the paper by Marvin Zelen, the details of which have been given in the references for this module. For some modules now, we have been studying the concept of the clinical trial, or rather, the controlled clinical trial. As you know, this is a double-blinded, placebo-controlled, randomized controlled trial. It is considered to be the gold standard of study design, as many of the features which are mentioned in the definition are safeguards against any kind of scientific bias in the conclusions. You will appreciate that this is extremely necessary because we want to have sound proof that a medicine is indeed effective before placing it on the market. Or if it is not effective, then also we want to have conclusions which are not subject to any kind of bias. However, an interesting dilemma arises because we are dealing with human subjects in such trials. The interesting dilemma is that there are some ethical issues. Now, it is the same ethical issues which has forced us to place all the scientific safeguards which I have mentioned earlier, such as blinding, placebo control, and so on. However, from the same ethical considerations, we would also wish to avoid allocation of the less beneficial treatment if we consider a situation where the trial is proceeding sequentially and even before conclusion of the trial, we have some considerable evidence that one treatment is superior to another. So our purpose is to avoid placing more patients on the less beneficial treatment, but we want to do this without compromising on the scientific validity of the study. It is thus necessary to develop associated statistical methods, and there are some references which have studied this in detail. So, for example, Armitage proposes a series of closed sequential experimental plans for such a situation, and Scombe proposes an alternative formulation which is Bayesian in principle. Colton explores the same problem from a decision theoretic perspective and proposes a minimax rule. Cornfield, Greenhouse, and Halperin in private communications have further generalized the Bayesian approach. These are the assumptions which we shall make for the play the winner rule. Firstly, we shall assume that we are dealing with two treatments, which we shall denote by 0 and 1. Secondly, we assume that the trial is proceeding sequentially and that patients are entering the trial one at a time in chronological order. The outcome of the trial is either success or failure, and finally we assume that the probability of success or failure depends only on the treatment, that is, there are no other relevant covariates which influence the occurrence of success or failure. Under these assumptions, this is how the play the winner rule operates. A success on a particular treatment generates a future trial on the same treatment with a new patient. A failure on a treatment generates a future trial on the alternative treatment. This can be explained by using two statistical models. So, for example, we may consider an urn model and balls placed into the urn. So, a ball marked with a 0 is placed into this urn whenever success is obtained with treatment 0 or failure is obtained with treatment 1. Similarly, a ball marked with 1 is placed into the urn whenever success is observed with treatment 1 or failure with treatment 0. When a new patient enters the trial, treatment assignment is done by randomly drawing a ball from this urn. An alternative model, which is closely related though not exact, is the two-armed Bandit problem. You can see the paper by Smith and Pike for more details of this. So this problem considers a slot machine with two arms. When one arm is pulled, the machine will either pay 1 unit or it will pay nothing. We are assuming that the probability of a payoff is constant from trial to trial, and we wish to develop a strategy which will maximize the expected winnings. So, such a strategy is given by assuming that if the n-1th trial results in a payoff, that is a success, the nth trial will be made on the same arm. If the n-1st trial results in no payoff, that is a failure, the nth trial will be made with the other arm. Now note that there is a slight difference with the play the winner rule in that the outcome of the preceding trial is always known at the time of a particular trial. That is, we know the outcome of the n-1st trial at the point at which we are conducting the nth trial. This will not necessarily happen for a clinical trial. So this is a closely related concept to the play the winner rule, but not exact, and hence we shall refer to this rule as the modified play the winner rule. So here is the modified play the winner rule. We have two treatments, 0 and 1. Patients are being allocated to treatments in a sequential order. At the first stage, we randomly allocate the first patient to treatment 0 and we observe a success for this patient. Having observed a success, we allocate the second patient also to the same treatment and again observe a success. As a result, the third patient is also allocated to treatment 0. But at this point, we observe a failure and hence we switch allocations to treatment 1. We observe a success and hence the next patient is also allocated to treatment 1. The moment we observe a failure, which is in the next case, we again switch to treatment 0, and this is how the trial progresses. So note that we have a geometric distribution and the number of consecutive trials on any one treatment will be geometrically distributed because we keep testing until a failure is observed and then switch to the alternative treatment. So an equivalent way is to assign patients to treatments until a fixed number of failures, say F, has been reached on each treatment. So if we define F as the number of failures observed on each treatment, Ni as the number of patients on treatment I equal to 0 or 1, and Pi as the probability of success for treatment I equal to 0 or 1, Qi equal to 1 minus Pi, then since Ni is the sum of F independent identically distributed random variables, each of which has a geometric distribution, we can derive the ratio of the expected number of patients on each treatment as expectation of N0 by expectation of N1 is equal to Q1 over Q0. Note that this implies that more patients will tend to be observed on the treatment which performs better. Suppose F failures have been observed for each treatment, then the joint distribution of the number of patients on each treatment is easily derived to be the first expression given on this slide. Now, one way to test the hypothesis of equality of the two treatments is to use this distribution under the condition that P0 is equal to P1 is equal to P. However, we will continue to have the nuisance parameter P. So instead, we can eliminate a nuisance parameter by considering the conditional distribution of N0 given the total sum N equal to N0 plus N1, which denotes the total number of patients treated. This probability mass function is given by the second term on this slide. Note that the conditional distribution depends only on the ratio of success probabilities lambda equal to P0 by P1. Of course, if lambda is equal to 1, then under H0, this simplifies further into the usual hypergeometric distribution. Now we can derive the generating function for this distribution, hence the cumulants and the first two moments. If log lambda is small or capital N and F are large, then we can approximate these and get expressions M1 is equal to expectation of N0 given N equal to capital N over 2, and sigma 1 square equal to variance of N0 given N0 plus N1 equal to N is N into N minus 2F by 4 into 2F plus 1. We can use this to get approximate confidence intervals for lambda by basing it on the normal distribution of N0 with mean M1 plus sigma 1 square log lambda and variance sigma 1 square. This results in the confidence interval given on the third line of this slide. If we wish to perform exact tests of inference, then these can be based on the probabilities, probability N0 greater than equal to N0 given N. We can do this using the hypergeometric point probabilities. Note that the modified play the winner rule is not practical in most clinical trials because there is usually a delay from the point that a patient is allocated a treatment to the point that the outcome of a trial is known, and several other patients may have accumulated in this interim time. However, the play the winner rule and the modified play the winner rule are only lexicographically different. That is, for the modified play the winner rule, Success or failure in a trial determines allocation in the immediately following trial. For the play the winner rule, this is similar except that this may not happen in the immediately following trial, but in some future trial. So it is only the order of allocation which is different, and as such the likelihood and any probabilistic properties of the two rules are identical. Now, in situations where a PWR allocation is not possible, that is, if all the known outcomes have already generated assignment to a treatment, then we can use a non-PWR rule. So one is to choose the treatment with probability half, or to choose the treatment so that the non-PWR assignments have an equal number on both treatments. In either case, the non-PWR assignments can be regarded as the first patient in a PWR trial, and the entire clinical trial will be made up of several parallel PWR trials. So assuming that we have k parallel PWR trials, the probability mass functions are as given on this slide. Note that the likelihoods are identical, and hence we get the same marginal distribution as for the MPWR. We may wish to generalize the PWR and the MPWR to the case when success probabilities are not constant. Note that we have assumed for simplification that success probabilities depend only on the treatment, but in some situations this may vary on patient or hospital characteristics, and in such situations the patients within each group may be stratified. So this stratification could be based on age or sex or prior disease status or hospital or so on. So treatment comparisons are going to be made within each strata as we have comparable subgroups. Let PIG refer to the success probability of the ith treatment for the gth subgroup. We assume that the probabilities can be written as the product of two terms. The first term depends on the subgroup, that is alpha of G, and the second term depends on the treatment. So thus Pi of G is alpha of G into Pi for I equal to 0 to 1 and G equal to 1, 2 to capital G groups. Now note that the ratio lambda equal to P naught of G by P1 of G is then equal to P naught by P1, and thus dependence on group is eliminated. So the expectation, variance, cumulants, etc. are as before for the case when we have stratified data. An interesting application of this problem is to allocate capital N patients to one of two treatments. Now the total number of patients capital N is sometimes referred to as the patient horizon, and the problem is to determine small n such that allocation is made in two stages. The first stage consists of assigning n by 2 small n by 2 patients to each treatment. Once this is done, the experimental information is used to determine which is the better treatment, and in the second stage we assign the remaining capital N minus small n patients to this better treatment. This has been considered in the literature by several authors such as Anscombe, Colton, Cornfield, Greenhouse and Halperin, also by Canna. To solve this problem, we shall define a utility function. Now, in prior cases, investigators have used a gain function which is proportional to the expected proportion of patients assigned to the better treatment times the difference between the treatment means. Zelen in his paper considers as the utility function the expected proportion of success. Note that both utility functions result in the same optimum value. That is, if we maximize the expected proportion of patients on the better treatment, it is equivalent to maximizing the expected proportion of success in the trial. So let us define Zn equal to 1 if the nth patient receives treatment 1 and 0 otherwise. We now have a Markov chain with two stages. So probability of Zn equal to 1 given Zn minus 1 equal to 1 is equal to P naught, and probability Zn equal to 1 given Zn minus 1 equal to 0 is equal to Q naught. So the matrix of transition probabilities is given by P naught, Q naught, Q1, P1. Using the asymptotic theory of Markov chains, we can calculate the asymptotic mean and variances for the number of patients on each treatment, and hence the expected number of successes in the first stage, as well as the expected proportion of success in the entire experiment. So U is approximately equal to small n by capital N into P naught Q1 plus P1 Q naught by Q naught plus Q1 plus capital N minus small n by capital N into P naught times probability of N naught greater than N1 plus P1 times probability of N naught less than N1, where we are assuming that the probability of exact equality of N naught and N1 is negligible. If we use the fact that capital N naught follows a normal distribution with mean and variance, then as derived, then we can write probability N naught greater than N1 as Qx, where Qx is 1 over root 2 pi integral z to infinity e to the power minus half t square dt. X is as given on the last line of this slide. U then can be written in the form of a weighted average W into P bar plus 1 minus W into P double bar. P bar and P double bar are the expected proportions of successes in the first and second stage of experiment. An interesting question is then to determine under what situation is P double bar greater than P bar. That is, under what allocation or what value of n can we expect more successes in the second stage of the trial than in the first stage. This is given using the expressions for P double bar and P bar as the condition that n is greater than equal to x alpha square into alpha 1 minus alpha by alpha minus half square P naught plus P1 by Q naught plus Q1, assuming alpha is not equal to half. So this is a summary of the PWR and MPWR rules. For more extensions, consider the references given in this module, which consider extensions to more than 2 treatments, introduce probability distributions for the time to response, which depend on the kind of response and the treatment, consider variables such as survival time or time to remission variables instead of just dichotomous outcomes, and generalize this 2-stage procedure to case stages, where at each stage one could either continue to use the PWR or place all patients on the treatment inferred to be the best. In this paper, we visited the Play the Winner rule, which is due to Marvin Zelen. The rule was decided in response to an interesting ethical consideration which arises when we deal with clinical trials, which is, what should one do when we see clear evidence of treatment superiority even before conclusion of the trial? We should ethically try and allocate more patients to the better trial, but we should at the same time be mindful of the fact that the trial has not yet concluded, that we have not yet received the targeted sample size and hence cannot claim to have the required power. A solution to this is provided by the play the winner rule, which we have studied in detail in this module. We have also studied a closely related concept called the modified play the winner rule, which is simpler in mathematical calculations. We have studied the properties of these two rules and seen how they can be used to get an optimal point at which the study can be terminated and allocation can be made to the better treatment.